In computing, an arithmetic logic unit is a combinational digital circuit that performs arithmetic and bitwise operations on integer binary numbers. This is a contrast to a floating point unit, FPU, which operates on floating point. It sounds really hard, but it's not. So what's an ALU in more understandable terms? Well, ALU stands for Arithmetic Logic Unit. Here's what it looks like from a schematic standpoint. You've got two operands, A and B, which are 2 of 3 of our parallel data buses. A and B are two 4-bit sums, anywhere from 0000 to 1111. Together they produce Y, your integer result, our third data bus. Y here is a 4-bit term and a carry. So, what's a data bus? A data bus is essentially a communication system that transfers data inside a computer or between computers. Think of it instead like a data highway of sorts. It just takes data and transfers it from one place to another. Like I mentioned, A and B plus Y that we've seen in the schematic are 3 parallel data buses. So opcode and status. Opcode input is a parallel bus that conveys to the ALU what operation to perform. In this case, it's our selection lines and carry-in, which tell the ALU to do one of its many either arithmetic or logic-based operations. So what's the status signals? The ALU status signals are carryout, 0, negative, overflow, and parity. So what's that mean? Carryout just conveys the carry from a resulting addition operation, the borrow resulting from a subtraction operation, or the overflow bit from a binary shift. 0 indicates all the bits of Y are 0. Negative indicates that the result is negative. Overflow indicates that it's exceeded the numeric range of Y, and parity tells you if it's even or odd in logic 1. So what can the ALU do? Oh my god, don't get me started. The arithmetic operations it can do include adding A and B, adding A and B with a carry, subtracting with a borrow, 2's complement, increments for A, increments for B, decrements for A, and decrements for B. So what about the bitwise logic operations? Well, this ALU can do AND. The bitwise AND, which is basically A and B appearing at Y, can also be used to test the bits. Next, it can also do OR, exclusive or XOR, and a 1's complement. So this is my model or project of my 4-bit ALU. In this project, I've used a 4069 IC as a hex inverter, 2 74153s for the MUXs, and a 74283 as my full adder. Here's a closer look at the breadboard. Looking closer reveals how I've used separate wires for selection 0, 1, and my carry-in bit, all my pink ones being my A inputs from A0 to A3 and B0 to B3 in blue. Here are some quick demo photos, 1+1 and an increment. For more detailed demo pictures, a more detailed guide on how I accomplished this project, and what I learned, check out my Medium article linked in the description. Thank you so much for watching, and as always, stay sharp.